Lesson: Key Concepts and Terminologies. Artificial intelligence and cybersecurity are two critical domains that have seen significant advancements and integration in recent years. AI's theoretical foundations provide a robust framework for enhancing cybersecurity measures, making it imperative to understand key concepts and terminologies within this intersection. AI, with its ability to process vast amounts of data and identify patterns, offers unprecedented capabilities in threat detection, prevention, and response. In the context of cybersecurity, these capabilities are harnessed to protect systems, networks, and data from unauthorized access, attacks, and damage. Machine learning is a pivotal concept within AI that plays a crucial role in cybersecurity. ML algorithms enable systems to learn from data, identify patterns, and make decisions with minimal human intervention. Supervised learning, unsupervised learning, and reinforcement learning are the primary categories of ML. Supervised learning involves training an algorithm on a labeled dataset where the input-output pairs are known, enabling the system to make predictions or classifications. In cybersecurity, supervised learning can be used for tasks such as identifying known malware based on historical data. Unsupervised learning, on the other hand, deals with unlabeled data, where the system tries to identify inherent structures or patterns without prior knowledge of the output. This is particularly useful in anomaly detection, where the system identifies deviations from the norm that may indicate potential security threats. Reinforcement learning, a third category, involves training an agent to make a sequence of decisions by rewarding it for desired actions and penalizing it for undesired ones. This approach can be applied in dynamic environments to adaptively respond to evolving cyber threats. Deep learning, a subset of ML, leverages neural networks with multiple layers to model complex patterns in data. DL has shown remarkable success in various domains, including image and speech recognition, and is increasingly being applied in cybersecurity. For instance, DL can enhance intrusion detection systems by effectively analyzing network traffic to identify malicious activities that traditional methods might miss. Natural language processing is another critical AI concept that has significant applications in cybersecurity. NLP involves the interaction between computers and human language, enabling machines to understand, interpret, and generate human language. In cybersecurity, NLP can be used to analyze textual data, such as logs, emails, and social media posts, to detect phishing attacks, social engineering attempts, and other threats. By processing and understanding language, NLP tools can identify suspicious patterns and alert security teams to potential risks. AI-driven cybersecurity also benefits from advancements in big data technologies. Big data refers to the vast volumes of data generated from various sources, characterized by its high velocity, variety, and volume. In cybersecurity, big data analytics allows for the processing and analysis of massive datasets to uncover hidden patterns and correlations that can inform security strategies. For example, by analyzing network logs, user behavior data, and threat intelligence feeds, AI systems can predict and mitigate potential attacks more effectively. The concept of threat intelligence is integral to AI-enhanced cybersecurity. Threat intelligence involves the collection, analysis, and dissemination of information about potential or current threats to an organization's security. AI can augment threat intelligence by automating the analysis of vast amounts of data from various sources, including the dark web, to identify emerging threats and vulnerabilities. This allows organizations to stay ahead of adversaries and proactively defend against attacks. Another vital concept is behavioral analysis, which focuses on understanding the normal behavior of users and systems to detect anomalies that may indicate security incidents. AI algorithms can continuously monitor and analyze user activities, network traffic, and system performance to establish baseline behaviors. Any deviations from these baselines can trigger alerts for further investigation. For instance, if a user suddenly accesses sensitive data at unusual hours or from an atypical location, it may suggest a compromised account or insider threat. The integration of AI in cybersecurity also brings forth the importance of ethical AI and fairness. As AI systems increasingly influence security decisions, it is crucial to ensure that these systems operate ethically and do not perpetuate biases or unfair practices. Bias in AI models can arise from biased training data, leading to discriminatory outcomes in security measures. For example, if a facial recognition system is trained primarily on images from a specific demographic, it may perform poorly on individuals from other demographics, leading to false positives or negatives in security contexts. Ensuring fairness and transparency in AI models is essential to maintaining trust and effectiveness in cybersecurity applications. The concept of adversarial machine learning highlights the dynamic and evolving nature of AI in cybersecurity. AML focuses on understanding and defending against attempts to deceive or manipulate AI models. Attackers may craft adversarial examples input data specifically designed to cause AI models to make incorrect predictions or classifications. For instance, adversarial attacks on image recognition systems can cause them to misidentify objects, while similar techniques can be used to evade malware detection systems. Researchers and practitioners must continuously develop robust models and defenses to counteract these adversarial tactics. AI's application in cybersecurity is not without challenges. One significant challenge is the explainability of AI models. Many AI algorithms, especially deep learning models, are often considered black boxes due to their complex and opaque nature. This lack of transparency can hinder trust and accountability, as security professionals may find it difficult to understand and justify the decisions made by AI systems. Developing methods to explain AI model predictions and actions is crucial for their effective deployment in security operations. Another challenge is the scalability of AI solutions in cybersecurity. Cyber threats are constantly evolving, and the volume of data to be analyzed is growing exponentially. AI systems must be scalable to handle these increasing demands and provide timely and accurate insights. This requires continuous advancements in computational power, data storage, and processing capabilities. AI also plays a vital role in automating incident response and recovery. In the event of a security breach, timely and effective response is critical to minimize damage and restore normal operations. AI-driven automation can streamline incident response processes, such as identifying the root cause of an attack, containing the threat, and initiating recovery actions. For example, AI can automatically isolate compromised systems, apply patches, and restore backups, reducing the time and effort required from human responders. The concept of zero-trust architecture aligns with AI-enhanced cybersecurity by emphasizing the need for continuous verification and monitoring of all users and devices, regardless of their location. ZTA assumes that threats can exist both inside and outside the network perimeter, and therefore, no entity should be trusted by default. AI can facilitate ZTA by providing real-time monitoring, adaptive authentication, and anomaly detection, ensuring that only legitimate and authorized activities are allowed. AI's integration into cybersecurity also necessitates a focus on privacy and data protection. AI systems often require large amounts of data to train and operate effectively. Ensuring that this data is collected, processed, and stored in compliance with privacy regulations, such as the General Data Protection Regulation, is essential to avoid legal and ethical issues. Privacy-preserving techniques, such as federated learning and differential privacy, can help balance the need for data access with the protection of individual privacy. In conclusion, the theoretical foundations of AI provide a comprehensive framework for enhancing cybersecurity measures. Key concepts such as machine learning, deep learning, natural language processing, big data analytics, threat intelligence, and behavioral analysis are instrumental in developing advanced security solutions. Ethical considerations, adversarial machine learning, explainability, scalability, incident response automation, zero-trust architecture, and privacy protection are critical aspects that must be addressed to ensure the effective and responsible use of AI in cybersecurity. By leveraging these concepts and addressing the associated challenges, organizations can significantly improve their ability to detect, prevent, and respond to cyber threats, ultimately enhancing their overall security posture.